Hello viewers, we have another interesting question on the applied mechanics. And so the question is, a screw jack carries a load of 400 kilogram. It has a square thread single star screw of 20 millimeter pitch and 500 millimeter main diameter. The coefficient of friction between the screw and nut is 0.22. And then we are asked to calculate the torque to rest the load and the efficiency of the screw. We are also asked to find what is the torque to lower the load. So we are asked to find three different things. So when you are given a question of this nature, the first thing you do is to take down your parameters. So you can say given we have pitch P equal to 20 millimeter. We have diameter D equal to 50 millimeter. You can convert this one to be 0.05 meter. This one can be converted to 0.02 meter too. And so we have that our weight, which is equal to mass times acceleration due to gravity, will be equal to mass is, okay, our mass, we can say mass M equal to 400 kilogram, so that our weight, G, acceleration due to gravity, G is given by 9.81, so our weight will be 400 times 9.81, and if we punch our calculator, this is going to give us 3294 Newton. So having done that, we can start. Okay, let's still take down a coefficient of friction. Our coefficient of friction mu is equal to 0.22. Okay, and so we know that helix angle of the thread is given by this formula. Helix angle of the thread, which is tan theta equal to P over pi d. And so if we have to solve this, our P is what? 0.02 divided by 3.142, pi is 3.142, times our D is 0.05. So if we punch our calculator, that will give us 0.02 divided by 3.142 times 0.05. So that will give us 0.127. 0.127. So at tan theta equal to 0.127, it means that theta will be tan inverse of 0.127. And so when we punch our calculator to find the tan inverse of 0.127, we have 7.23 degree. And so with this, we also know that the angle of our friction phi, okay, we've taken that one, and we know that tan phi, angle of friction, tan phi, the first one is theta, this one is phi, which is equal to the same thing as mu, equal to 0.22. And so because we are looking for phi, our phi will now be tan inverse of 0.22. So when we find the tan inverse of 0.22, punching our calculator, we are going to have 12.4 degree. So with that, we can start finding first the torque to rest the load, and then secondly the efficiency, and then lastly the torque to lower the load. So we say to determine the torque to raise the load. So we to determine the torque to raise the load. So the torque to raise the load is given by this formula, 1/2 WD tan into phi plus theta. So this 1/2 is the same thing as 0.5 times our weight. This is the value for our weight. We've calculated weight is 3924. So times 3924 times our D is 0.05. We've converted it. 0.05 tan into phi is 12.4 plus our theta is 7.23 degree. And so when we multiply this by this and by this using our calculator, we are going to have 98.1 tan 98.1 tan into this plus this will give us 19.62. And so when we now multiply 98.1 tan times tan 19.62, our answer becomes 34.9 Newton meter. So what this implies is that the torque needed to raise the load up will be 34.9 Newton meter. Torque, Newton meter. So we are done with that. And so the second part of the question is to calculate the efficiency to determine the efficiency. So to determine the efficiency, we know that the efficiency is given by this formula, tan theta all over tan into phi plus theta. So this will be equal to tan, our theta is 7.23, divided by tan into phi. We know that our theta is 7.23, phi is 12.4, and plus our theta is 7.23. So this will give us tan 7.23 divided by tan 19.62. And so when we calculate this, we calculate this, we are going to have 0.126 divided by 0.356. This will give us 0.353. And so since we are talking about efficiency, we can multiply it by 100. And so this will give us 85.4% approximately. So it means the efficiency will be 35.4% approximately. 35.4% approximately. So having calculated the efficiency, we can now look into calculating the last part of the question, which is to find the torque to lower the load. Torque to lower the load. And so this is given by the formula 1/2 WD tan into phi minus theta. So this will give us 1/2 is the same thing as 0.5 times, we know that our weight, we've calculated our weight here. We've calculated our weight here to be 3924 times our diameter is 0.05. We have it converted here. Tan into, so this will give us, our phi is 12.4 and it is minus 7.23. It's minus theta, so theta is 7.23. So when we multiply the whole of this, we are going to have 9.98.1 times this minus this will give us tan 5.17. And so this will be equal to 98.1 times, when we find the value of tan 5.17, that will give us 0.0904. So when we multiply this by this, we have 8.87 Newton meter. So which means the torque to lower the load will be 8.87 Newton. And then if you check, our torque to raise the load will be 34.9 Newton meter. So which means a higher torque is required to raise the load up, than when it is required to lower the load. So viewers, this is how to go about a problem of this nature. This is how to solve it. We've gotten to the end, so let's take a review from the beginning. This is how it looks like, and I hope that is taken. And then the remaining part of the solution, that is to define the efficiency and the torque. So from our answers, we know that the torque to lower the load is lesser than the torque required to actually raise the load. Thank you.